Hello, it's Mr. Claudia here, and today we are going to continue looking at limits. This time we're going to look at what happens when we have the limit of something towards infinity. So we're going to have a little bit of a long talk just looking at exploring this idea, and then at the very end we'll get to some practical strategies. So first, consider a sequence defined like this. So a sequence u sub n, and then we sub in different values of n. So let's start with n equals 1. That would mean u1, u sub 1 is 1 over 1 plus 1, which gives me half. Okay, n equals 2, well that would be u sub 2, which is 2 over 2 plus 1, which gives me 2 over 3. N equals 3, u sub 3 is equal to 3 plus 1, which gives me 3 over 4. Hopefully you see the pattern here, what's happening. I could write the sequence. We can write the sequence. So it would be half, 2/3, 3/4. If you follow the pattern, it'd be 4/5, 5/6, and dot dot dot, because it goes on forever. Now, if I had to graph this, if I graphed it with terms, so my first term, my second term, my third term, my fifth term, so these are my terms. It's not really a function, right? It's a discrete bunch of terms. Okay, if I want to graph these, it looks like the top is going to be 1. This is going to be half. So my first term is half. My second term is 2/3, so it's somewhere here. My third term is 3/4, so it's somewhere here. Then I have 4/5, sorry, I haven't drawn this correctly. Somewhere here and somewhere here. Each one's getting closer and closer, but it never really reaches 1. So we almost kind of see that asymptotic behavior. Getting closer and closer to 1 but not touching. So when we talk about this sequence, we say that it gets closer and closer to 1, it converges. This sequence converges to 1. Why don't we say limit equals this, but or why is we're not saying asymptote? It has to do with the fact that it's a sequence. It's just discrete points. So we say a sequence can converge to 1 in this case. Another way of thinking of the sequence, though, if it wasn't a sequence and it was more of a function, this sequence approaches the fixed limit of 1. If I had a function, it's actually approaching 1. So we could say the limit of this sequence as the number of terms approaches infinity is 1. Neat. No matter how many terms I have, even if I have n equals 1,000,000, it's still going to be less than 1. Okay, let's look at another sequence. The Fibonacci sequence. Maybe you've heard about this one. It's really cool. It's a recursive sequence where each term is the sum of the 2 preceding terms. So term 1, u1, is 1. u2 is also 1. Now, un is the term n minus 1 plus n minus 2. So, for example, if n equals, actually I'm going to write this out, so I'm not going to explain it. The first term is 1. The second term is 1. Now, u3, well, I use this formula. So u3 is going to be u3 minus 1, which is 2, plus u3 minus 2, which is 1. So to find u3, I have to add up u1 and u2, which gives me 2. So that's how it worked. I added the 2 previous values. u4 is going to be, again, you could use this formula, u3 plus u2, or you could just add the numbers. 2 plus 1 is 3. u5 is equal to u4 plus u3, which is 5, etc., etc., etc. before we go any further, the Fibonacci sequence is really neat. It's one of those beautiful math things. You see this sequence a lot in nature. A lot of people think it's really cool. For example, if you look at the number of branches in a tree, and you just keep going up through the tree and doing a cross-sectional line, you'll find that the number of branches tends to follow a Fibonacci sequence. So you end up with 1, then 2 branches, then 3, then 5, then what's the next one? 8. When you look at how pine cones are arranged, and you can count the number of pine cones, number of rows or concentric circles, tends to follow Fibonacci sequence. So we see it a lot in nature. So this sequence, though beautiful, when I write it out, 1, 1, 2, 3, 5, what's next? 8, 13, 21. Is that getting closer to a fixed limit? If I look at the millionth term, is it going to approach something? No way. It does not approach a fixed limit. In other words, it gets bigger. It blows up. It gets bigger and bigger. Therefore, it is divergent. My favorite film. In other words, we say the limit as the number of terms approaches infinity for the Fibonacci sequence is equal to infinity, positive infinity. And therefore, I say it does not exist because infinity is not a fixed limit. Right? Oh, the limit is infinity. Well, no, it can't be a limit if it's infinity. Like infinity is not a limited number. It's some value that is some idea. It's bigger than the biggest number that is possible. So it's impossible for infinity to be a limit. So I would say that this limit does not exist. So let's just talk about sequences. Are these series or sequences convergent or divergent? 0.3, 0.33. So we see the pattern. I keep adding 3. And I would say, yes, it's convergent. We're getting closer and closer to a third. So the limit as n approaches infinity of this sequence is a third. What about this sequence? 1, -1, 1, -1. It's oscillating back and forth between the two. Is it getting closer to a fixed number? No. So it's divergent. It is not approaching a fixed limit. It's just oscillating. Okay. So that was a little bit of a preamble looking at different types of sequences. Sequences and series are in the IB curriculum, but I just talk about divergent and convergent sequences here because it's relevant to what we're looking at. Eventually, we're going to be looking at limits approaching infinity. So it is better to think of a limit at infinity as a sequence. So when we get questions like this, the limit of a function as n approaches infinity, it's easier to think of it as a sequence. The sequence, so in this case, it would be 1 over 1, then 1 over 2, then 1 over 3, 1 over 4, 1 over 5, dot, 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 dot. So as n gets larger, as my n numbers get bigger, this 1 over n, well, it starts at 1, then half, then 1/3, 1/4. It's getting smaller and smaller. Graphically, if I were to draw this, I mean, this is a rational function, technically, right? And it starts off with a big number, and as n gets larger and larger, or x gets larger and larger, my function approaches an asymptote here. It's just to kind of help our understanding. So the limit of 1 over n as n approaches infinity is equal to 0. So this is one of two very special limits we're going to use when we start doing practical questions. The limit of 1 over n, or in fact, the limit as n approaches infinity of 1 over n to the power of r is equal to 0 if r is greater than 0. And that's a rule. That's kind of why we showed you that one. We'll show you on the next page why this is so practical, but basically, if you have some sort of function where it's n approaches infinity and you have n in the denominator, then that limit of that is going to be 0. It's coming down to 0. The other important sequence is this one, and we're going to see how this is practical as well. So if I have this, remember we think of it as a sequence, so half to the power of n, and n is increasing. So the sequence is going to be 1 over 2, then 1 over 2 to the power of 1, 1 over 2 to the power of 2, which is 1/4, 1 over 2 to the power of 3, which is 1 over 8, 1 over 16, 1 over 32, dot, 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 dot. So I think we can see that this starts large and then gets very small, right? This sequence, just like the last one, approaches 0. The limit as n approaches infinity is half to the power of n. That limit is 0. Now graphically, this is actually an exponential curve. Well, it's an exponential decay. So it's something like this. Right? If you had to imagine kind of the function that was analogous to what we're doing with sequences, and again, there's an asymptote here. So it's the same sort of thing. As you approach n equals infinity, the function, or this approaches 0. So we have another rule. Oh, I see, I forgot to write this here. We develop the rule, and we develop the rule. The limit as n approaches infinity, r to the power of n is equal to 0 if r, the absolute value of r, is less than 1. Let me just put that in a box because this is a rule. So the limit of r to the power of n is equal to 0 only if r is less than 1, or the absolute value of r is less than 1. In other words, this is saying r is a proper fraction. So if it's r is negative half, the absolute value is still less than 1, so it would still be valid. These are two sequences, or you can think of them as functions, where the limit approaches infinity, where as x approaches infinity, the limit approaches 0. These are the two useful ones. We're going to come back to these. Let's turn the page. We're almost at the part where we're going to be able to apply this. Just before we go any further, we should just stop and talk about infinity. So when you were first taught about infinity, you were told it's a very large number. That's not really totally true. Infinity is the number greater than the largest countable number. So infinity is not just a really, really big number. Infinity is the number greater than the largest number we can count to. So this is a very theoretical idea. It's not a number at all. It's an idea. It's a place. It's a place that we can never go to, but we can imagine. Just like we can never reach an asymptote, we can never count to infinity. You think about infinity in popular culture, like Buzz Lightyear, to infinity and beyond. Like, well, that's impossible, right? That's why it's such a great expression. There's the Chuck Norris jokes. You know, he was this martial arts movie guy in the 80s, and you know, they made all these jokes about him. They're very funny, but one is like Chuck Norris counted to infinity twice, and these jokes are supposed to show how like such a bad guy he is. So anyways, you can get the joke, right? Because this is impossible. You can't count to infinity. Finally, again, we're just about ready to do some real questions, but if I were to ask you the limit of n squared minus n, you might be, if you didn't know any better, you would say, okay, well, all I know about limits is what Mr. Claudy told me, which is, sorry, this should be in brackets, which is I can sub in, maybe I'll try direct substitution. If we sub in n equals infinity, well, then I end up with infinity squared minus infinity. Now, remember, I just told you infinity is not a number. So how do you take the largest countable number, then you square it, then you subtract the largest countable number? Like, does this equal 1 infinity, half infinity? Like, I have no idea. And so this is really confusing. This is why when we're solving limits at infinity, we can't just do direct substitution. What you have to do instead in this question is factor out an n, so you're left with n minus 1. Now when you do direct substitution, you get infinity, n, right? You're subbing in infinity, and then infinity minus 1, which is still infinity. So you end up with infinity times infinity, which is still infinity. It's not you get infinity squared, you just get the largest number times the largest number is still the largest number. So you get infinity. And we know that the limit, if the limit is infinity, then it does not exist. What about this question? Again, if I sub in infinity, well, let's see what happens. First of all, let me cancel out the n's here in the numerator and denominator. So I end up with n over negative 5. Let me sub in infinity here, so I get infinity over negative 5. Well, the largest number in the world divided by a negative is going to be the negative largest number in the world. So again, the limit does not exist. So be really careful about treating infinity as a variable and just subbing in infinity. That's not really the way we solve most limits at infinity. Here we finally, it all comes together. This is our strategy. To find the limits at infinity, we divide the numerator and denominator by the highest power of n in the denominator. Watch why this works. So let's say I ask you this limit. This limit's different than the ones you did the past 2 lessons because it has n approaching infinity. We use our strategy. We divide the top and bottom by the highest denominator of n in the denominator. So I have n squared in the denominator, so I'm going to divide the top by n squared, and then I'm going to divide the bottom by n squared. This is very messy, right? Let me just make a note here. Divide top and bottom by n squared. Okay, so now when I do that, what happens? Well, now technically this is n squared over n squared minus n over n squared. That's my numerator. Hopefully that makes sense to you. I've just taken a fraction that's being subtracted, and I've with a common denominator, and I've made it so that they're not, with the denominator, and I've made it so that they're separate. So if you think about how would you solve this, well, because they have the same denominator, you would just subtract the numerator. But I split it back. I went backwards. Similarly, the denominator is 2n squared over n squared plus 1 over n squared. Now I'm going to simplify a little bit here. So n squared over n squared is 1 minus 1 over n over 2, because those cancel out, plus 1 over n squared. Okay, now finally it all comes together. We can use the properties from the other page. Or specifically, remember this property? the limit of 1 over n, or 1 over n to the power of anything, is equal to 0. So when I do direct substitution, I know, just for this one question, I'm going to show you actually. Let's do each of these limits individually. So limit of 1 minus the limit of 1 over n. So I'm just distributing my limit property. Remember the first day we did limits, I kind of showed you all the different properties and that you're allowed to do this. Okay, so now I can actually, the limit of 1 as n approaches, well, it's always 1. The limit of 1 over n, that's the property from the other page, that's 0. Limit of 2 is 2, and the limit of 1 over n squared, well, even as long as it's in the denominator, it's also 0. So my limit then is half. This sequence converges to half, or this function, as n approaches infinity, reaches 0, or reaches half. The strategy, again, was to divide by the highest power of n in the denominator, and then you can use that property from the other page. Okay, let's do the next one. So here I'm going to divide top and bottom by n, because that's the highest denominator, the highest power of n in the denominator. So I end up with n squared over n plus n over n, 3 over n minus n over n. Divide top and bottom by n. Great. Now I can rewrite this. So I have n squared over n, that's just n plus 1, 3 over n minus 1. Okay, now we can do my substitution. Well, the limit of n, if you did direct substitution, it'd be infinity plus 1 over, this one would become 3 times 0, right? Because the 3 is like a constant in front, and the limit of 1 over n is 0, like we just did. We just showed. Minus 1. So you end up with infinity plus 1, which is just infinity, over 0 times, which is negative 1. So you end up with negative infinity. In other words, it does not exist. Oh, here so I didn't show this well, but 3 over n is really 3 times 1 over n. So the limit of 3 is just 3, but the limit of 1 over n is 0. Anyways, and then when we did all the work, we got negative infinity, so it blows up. It doesn't converge. There's no limit. Ooh, okay, 2 more. What about this question here? The limit as n approaches infinity. Okay, well, I want to divide by the highest power of n in the denominator. It's probably better if I expand first, just to make this a little cleaner. So I have n plus 1, n squared plus 5n plus 6. Oh no, I dropped my pen. Okay, hang on. So I expand. Okay, now I can divide top and bottom by n squared. So I have n over n squared plus 1 over n squared all over n squared over n squared plus 5n over n squared plus 6 over n squared. Let me simplify that a little bit. So I have 1 over n plus 1 over n squared over 1 plus 5 over n plus 6 over n squared. Okay, and now let me do my substitution. Well, we know from the property that this is equal to 0 plus 0 over 1 plus 0 plus 0. So we end up with 0 over 1, which is okay. That's just 0. So there is a fixed limit there. The fixed limit is 0. Okay, last question. Similar type of question. I need to expand this first. So I have 4n to the power 4 plus 5 over 2n to the power 4. So minus n and then minus 4n squared. So it's minus 5n squared plus 2. And now I want to divide top and bottom by n to the power 4. So I have 4n4 over n4 plus 5 over n4 all over 2n4 over n4 minus 5n squared over n4 plus 2 over n4. Whew, okay, now I'm going to rewrite simplified version. So I have 4 plus 5 over n to the 4 over 2 minus 5 over n squared, I think, plus 2 over n4. Now when I do my direct substitution, I have 4 plus 5 times 0 over 2 minus, this is going to be 0, this is going to be 0. So I get 4 over 2, which is 2. We should just say, so that's that. That's how we find the limit at infinity. Again, we thought of it as sequences, but now we can use it with functions. If you want to tie this back to functions, we're technically finding, when we find this a fixed limit as n approaches infinity, we're actually finding what happens with a horizontal asymptote, right? Like this function, if I were to graph it, it looks something like this. It's kind of got this cool shape, like so what we've really found is, well, what happens to this function as x approaches infinity? So as you go along x, a very, very large number. And what is happening is the y value, or the limit, is approaching 2. Oh, so that's not 2. Sorry, it should approach 2, not 0. And so that's kind of a measure of the horizontal asymptote. It's all kind of related. The important thing is that you can find limits as n approaches infinity, and you do that using my strategy where you divide the top and bottom by the highest degree of the variable in the denominator. Your homework is on a separate sheet of paper. It's number 1 to 3. And just a note, it continues on the back. So it's like 2 pages. Oh, there it is. Okay. Good luck, and we'll see you next time.